Section 1.4, Types of Functions. These are a list of topics we will be covering in this section. The first one we're talking about is what's called a constant function. And a constant function is defined to be f of x is equal to b, where b is some constant or fixed number. Examples of this could be f of x equals 5 or f of x equals negative 2/3. Please notice the one thing we want to focus on is on the right hand side there is simply no variable. And the one of the things we also need to realize is that a constant function simply gives us a graph of a horizontal line. This function here, this f of x equal to 5, that corresponds to this top example. Notice that it crosses at the value of the constant 5 in this case. The second type of function we want to look at is what's called a linear function. In this case, the function f of x is equal to mx plus b, where m and b are constants. This is called the linear function. Here's an example. F of x equals 2x minus 3. F of x is equal to negative 2/3 x plus 4. The top example is actually shown in the graph here to the right. F of x equals 2x minus 3. Now please note the book uses a instead of m in the definition. And in the prior slide we looked at f of x equals 2. This would also be considered a linear function. Just in this case, your m would be 0. Please realize also that all linear functions have graphs that are straight lines, which would make sense because we saw the constant function had a graph which was a straight line also, which also meant that it was a linear function. Now, if we were looking at tabular representation, or a table of this function, f of x equals 2x minus 3, here I just picked the x values of negative 2, negative 1, 0, 1, 2, and 3, and I plugged in those into this function and got out the corresponding y values, negative 7, negative 5, negative 3, negative 1, 1, and 3. Please note that as x increases by 1 over here, from negative 2 to negative 1 is 1, from negative 1 to 0 is 1. Please note also that your y values increase by 2 each time. This is what's known as the rate of change of y with respect to x. So as y increases as x increases, please notice that in this case this is a constant rate of change. And this is actually a property of a linear function, that it will have a constant rate of change, that y will change consistently as x changes. Another name for this rate of change is what's called the slope, which we will study more in future sections. We will define it here though. The slope is defined to be m equals delta y over delta x, and we're going to take 2 points, x1, y1, x2, y2, like we did when we were defining midpoints, and distances. And whenever you see a delta means a difference. So delta y basically means the difference in the y, so y2 minus y1 over x2 minus x1. And this is going to give us a nice ratio, so the change in y over change in x, some of you may have memorized it as rise over run. The one thing we do require is that x2 not be equal to x1, because if x1 and x2 are equal, this is undefined. And this is simply what we're calculating. Here's your delta y, the height, the rise. Here's your delta x, the run. Simple example is this is to calculate the slope of the line between the points negative 2, negative 5, and 4, negative 3. We simply have to pick which one of these we want to be our first point, which one we want to be our second point. It actually does not matter. We just have to stay consistent. So we will let this 4, negative 3 be our second point, and the negative 2, negative 5 be our first point. So y2 is negative 3, y1 is negative 5, so negative 3 minus negative 5. x2 is 4, x1 is negative 2, so 4 minus negative 2. We have negative 3 minus negative 5 is actually 2, and 4 minus negative 2 is 6, so slope is 2/6. And whenever we have fractions we need to reduce, so 2/6 reduces to 1/3 is our slope. We can also look at a picture of a graph and get the slope of that line. There's a couple different methods we can use. One is to pick 2 points. In this case we have the point 0, negative 4, and the point 4, negative 2. So if we were to use our slope formula like we did in the previous exercise, this would be negative 2 minus negative 4 over 4 minus 0, which is 2 over 4, which is 1/2. The other thing we could do is do our rise. We go up 2, and then we go to the right 4, which is 2 over 4, which is 1/2. Here's an example of a linear function. It says the table below and the corresponding graph show the price of an order of penicillin based on number of vials. So the number of vials ordered are 20, 40, 60, 80, and 100. And the corresponding price are 100, 200, 300, 400, and 500. We're to actually plot these out. These would all fall on this line here. Now, y is a linear function of x. We can tell this based on two things. First, the graph is a straight line. Second, the slope is consistent. It has a constant slope of 5. If I were to actually take 2 points and calculate the slope, I took the first 2 points on my table, 200 minus 100 over 40 minus 20, which is 5. Other way we can tell from the graph is that it doesn't waver, it's a straight line, so we know if we pick any 2 points, the slope will be 5. But if we were to go back on our table and pick up any 2 other points and plug into our formula, we would get 5 as well. And what does this 5 mean? Well, this is 5 what? Our slope was changing in y. The y was measured in price. Over change in x was measured in penicillin. So it's really understood to be 5 to 1. So in other words, an increase of 1 vial in the order increases the price of the order by $5. So we increase $5 for every 1 vial. We do have functions that are not linear. Here's an example of f of x equals x squared minus 4. A couple ways to tell they're not linear is, number one, they don't make a straight line. We clearly do not have a straight line here. We have what's called a parabola, which we will study later in future chapters. Another way to do it is to actually take sets of points. In this case, I can take the first 2 points, negative 2, 0, negative 1, negative 3, plug this into our slope formula, and if I plug those 2 points in, I actually wind up with a slope of negative 3. Whereas if I take 2 other points, 0, negative 4, and 1, 3, negative 3, and plug those into my slope formula, you actually wind up with a slope of 1. Notice the slope here is not constant. It's not the same. And remember that the slope of a linear function has a constant slope. It does not change depending on the points that you plug in.